Welcome back. So the last time we were looking at directional, we defined differentiability, and we stated a theorem stating that a function is differentiable, right? The theorem was, if a function was differentiable, if f is differentiable at a, roughly speaking, I'm paraphrasing of course, then the directional, then df is precisely equal to this, and it is equal to the dot product of the gradient with h, which if you write it in its full glory, it's just this, right? In particular, all the directional derivatives exist. Okay, so how do you prove this? Okay, so what does differentiability mean? F of a plus h is f of a plus the derivative of f at a plus an error term, let's call this times the error term, where this error term goes to 0 as h goes to 0, right? Now what we can do is take h vector to be some small h, it's a scalar, times v for all small enough h. Why must h be small enough? Because then this vector will have small enough norm so that a plus h continues to lie in the domain of f. Notice that if you move very far away from a, you may not even lie in the domain. Okay, that's why I'm being a bit careful here. Okay, right. So so this h is small enough. What does that imply? So if you substitute this particular value of h and you divide by h, yeah. So f of a plus h times v minus f of a divided by h is dfa times h times v divided by h plus h times v divided by h, right? Okay, so well, what is this equal to? Right, so what's this equal to? This, the right hand side of this, if you wish, the right hand side is, by linearity this h pulls out, so it's simply, because it's a linear map, it's this plus mod h by h times norm v times e of a comma this. As h goes to 0, what happens? This goes to 0, whereas this stays bounded. What does that mean? If you take the mod of this thing, this is equal to the norm of v. So in other words, when h goes to 0, this goes to 0, this is less than or equal to some constant, which means this entire thing is sandwiched between the mod of this entire thing, the mod of this thing is sandwiched between 0 and something that goes to 0. So by the sandwich rule, this entire thing goes to 0, and therefore this limit exists. This limit, if I put a limit here, this limit exists and equals this, right? So not only does the directional derivative exist, it equals this, right? Now it seems formidable to prove that these two are equal, fine. The fact that this is equal to this explicit formula seems like a difficult affair, but actually it's not. It's much simpler than it looks, okay? So the point is, because we know that this is a linear map, because we know it's a linear map, So it's h1 e1 plus h2 e2, etc. Maybe I'll put a vector sign just to emphasize this. So it's by linearity, we get this. This is h1 times the directional derivative along E1 of f this is precisely by definition the partial derivative. Which is basically and the gradient. What is the gradient? The gradient is simply the collection of all partial derivatives put together as a vector. H vector dot the gradient vector is precisely this by definition. Okay. So this means that if a function is differentiable, not only is the total derivative unique, but also its directional derivatives exist and they can be computed using this nice little formula. So if you've heard of gradient descent in machine learning, this formula underlies it in some sense as to why it works. So here's a theorem, but we'll see that later. Okay. If a scalar field f is differentiable at an interior point, of the domain, point S or A, then f is continuous at A. So differentiability does imply continuity, as it ought to. If this theorem were false, then the fault doesn't lie with the theorem, it lies with the definition, that we made the wrong definition. Okay, so how does one prove this? We follow exactly, it's a scalar field, exactly the same strategy as in single variable calculus. We take this and we know what this is equal to. This is the derivative of plus the error term, if you so will. Now this is equal to h comma the gradient, if you will, plus this by the triangle inequality in fact there are many ways to do this, but we'll stick to this. By the Cauchy-Schwarz inequality, which is our best friend, this is less than this. Right. Now this goes to 0 as norm h goes to 0 by definition of differentiability. This goes to 0 as norm h goes to 0. So by limit laws, the sum of these things goes to 0 as norm h goes to 0. So by the sandwich theorem, this goes to 0 by the sandwich law. Okay. In other words, f is continuous. Okay. Yeah. So thankfully, differentiability does imply continuity. So we are in great shape. Okay. Now I'll just spend a few moments discussing the meaning of the word gradient. Why is this weird vector that we have arbitrarily defined? I mean, sure, the collection of partial derivatives, it's an important object, that much is obvious. Why is it called the gradient, right? When you think of the word gradient in English, it's supposed to tell you something about slope, right? You say something has a high gradient, that means it's very difficult to climb up, right? Okay, so let norm v be 1. Okay, so we are talking about genuine directional derivatives here. So this is equal to gradient of f times v if f is differentiable at the point. Okay, right. So mod of this is less than times norm v by Cauchy-Schwarz with equality holding if and only if is parallel to v for some c. So this norm becomes equal to this precisely when gradient of f is parallel to v, that is v in fact, if gradient of f is not 0, right, then v is proportional to is c times gradient of f, right. So what does this indicate? Okay. In fact, you can say something even better. So gradient of f is less than or equal to this and larger than minus this. Okay. And this equality holds when v is indeed grad f divided by mod grad f. Assume grad f is not 0, not the 0 vector. This when v is minus grad f by mod grad f. What this tells us is the direction in which you must move so that f increases the fastest. So as I told you, if you take a look at our, if you go back to our temperature example, if you were a mosquito and you were flying here, if you go in one direction, the temperature might increase fast, in another direction it might increase slowly and so on. So as a mosquito, if you were to ask the question, what direction must I move in for a little bit of time so that the temperature increases the most for me? Because mosquitoes generally they like hotter things, they don't like cold things. So in what direction must I move for a small amount of time so that the temperature increases the most for me? Well, that direction is precisely this. Okay. So if you move along the gradient of the temperature, in that direction the temperature increases the most. That is why the word gradient is used, because this is the direction of steepest increase. In fact, the opposite, the negative of this direction is the direction of steepest decrease. Okay. That's why it's called the gradient, because it's precisely that direction you must move in a little bit to make sure that f increases the most. If you want to make f decrease as much as possible, the best direction to move in is minus of the gradient. Okay. So for example, if you look at this function, let's say call this z, right. So this is say 25 minus x square plus y square. Okay. What would the graph of it look like in 3 dimensions? This is x, y and z. So when you take x equals y equals 0, you're at 25. When you take x square plus y square equals 25, on this circle you're 0. So it's like this. It's like a little mountain, right? Suppose you're trekking up this mountain. Suppose you're at this point. Okay. In what direction in x and y must you move so that you scale up the mountain fastest? Okay. morally in 3 dimensions you must move in this direction, right. So the gradient of this function is minus 2x is minus 2y, right. So for example, if we are located at this point 3 comma 4, then the gradient is minus 6 comma minus 8, which means if you minus 6 and minus 8 imply that you have to move in this direction. So in the x direction, if you move, so if you are here, that is if you look at it as a graph, if you move in this direction, then you will go up the fastest, right. So in that sense, it's the direction of steepest increase, okay, right. Okay, so this leads to a nice algorithm to minimize functions, and that's called the gradient descent, the famous gradient descent algorithm, which is ubiquitous in machine learning. Versions of these, if not exactly this, versions of the gradient descent are used even in large language models and so on and so forth. Before we go to that, let's now talk about differentiability, but not just of scalar fields, but of vector fields. Yeah, so we'll deal with differentiability of vector fields. Right, so what is a vector field? A vector field is simply a function, a vector valued function. Recall that f is said to be continuous at A if given epsilon greater than 0, there exists a delta greater than 0 such that whenever x minus a is less than delta and x lies in the domain, then f of x minus f of a is less than epsilon, right. And f is continuous if and only if each component fi is continuous. So vector valued function, it's continuous if and only if each component is continuous, okay. Right, so now we want to talk about the differentiability of a vector valued function. So let A be an interior point as always. Right. We can talk about the directional derivatives of f as well. F is said to have a derivative along V at the point A if this one variable function, if this vector valued but one variable function limit exists. Okay. Now once again it's easy to prove that this exists if and only if the directional derivative of each component exists for each component. Okay. So in other words, the directional derivative of A, right, is a collection of directional derivatives, one for each component, if you will. It's a vector this time, and so on. Okay. So in particular, we can talk about partial derivatives of each component and therefore the partial derivatives of this vector valued function. So that much is fine. Okay, there's nothing very shocking going on when it comes to vector valued functions, it's just a matter of bookkeeping. It's just a matter of taking the derivatives along for each component. And indeed, the definition of differentiability is also not very unexpected. F is said to be differentiable at an interior point at an interior point A, if there exists a linear map, as always, df, yeah, except the domain of this linear map is Rn, the range is a vector valued object, right, as opposed to a scalar valued object, such that the limit as h approaches 0, f of a plus h, basically we want to say f of a plus h is approximately f of a plus the derivative, right, but exactly as before, this is 0. Okay. The linear map df is called the derivative, or sometimes called the total derivative of f at a. F is said to be differentiable on an open set S, if df exists for all a in S. Okay. So this is the definition of differentiability, right? So once again, let me make one small remark here. So we are defining differentiability on open sets, right? But in one variable calculus, you can talk about the differentiability of a function on a closed interval by declaring it to be differentiable from the left on the right endpoint and from the right and the left endpoint, right? So can one extend the definition of differentiability to non-open sets? Yes, one way to do it is to take some arbitrary set S, take your favorite open set containing S, f is said to be differentiable on this arbitrary set if it can be extended to the open set containing S, and it's differentiable on this open set, right? So that's one way to define differentiability. Then we'll get into tricky matters like this. Suppose I choose a different open set and a possibly different extension of f, then will the definition of differentiability be well defined? Will the derivative make sense or not, and so on and so forth, right? These are tricky matters, so that's why we won't bother with these things right now at least, okay? But it suffices to know that on paper you can try to play this game for non-open sets by simply taking an open set containing this set and extending the function if it is possible, okay? All right. So here is an easy lemma. F is differentiable if and only if each component is so, okay? So that's not rocket science. I mean, what does it mean to be each component is so? That means that I want to say this goes to 0 for all I if and only if this goes to 0. Okay, this is very easy. It's exactly the same proof that, for example, a vector valued function is continuous if and only if each component is continuous. Okay, you don't need to put the norms, but you can still. Okay, so this you can prove, all right. Moreover, more importantly, this derivative at v is precisely the directional derivative of f. Again, how does one prove this? Well, we already know that this has to be the directional derivative of the ith component along. I mean, the dfi acting on v is the directional derivative of fi along the ith component, right? So df acting on v is a vector, right? What vector is it? It's a vector in Rm. What's the first component of this vector? It's just the directional derivative of the first component of f. What's the second component? It's the directional derivative of the second component, and so on, right? So if you treat the gradient to be a row vector, typically vectors for us are column vectors, but if you treat the gradient as a row vector, then this has a very nice interpretation using matrices. So if you treat, so the derivative is what it's, once again, if I write it in components, this is gradient of f dot v, gradient of f2 dot v, etc. So you can write it like this: Vn, this is an n by 1 matrix, these are m, this is an m by n matrix. The first row of the matrix is basically the gradient of f1. In other words, it's df1 dx1, df1 dx2, df1 dx3, and so on. The second row of this matrix is df2 dx1, df2 dx2, and so on. The last row is df, what is it? M dx1, df m dxn. Indeed, let's do a sanity check. Is this recovered? Well, what is the first entry? It's simply matrix multiplication is row by column. So it's df1 by dx1 times v1 plus df1 by dx2 times v2, and so on, which is precisely the dot product of the gradient of f1 with v. Okay. So this matrix is called a derivative matrix. Okay. Right. So again, once again, the convention for our matrix is as follows: every row is the gradient of each component of f1. So let's do an example. So if I take E as y comma minus x, these are both polynomials. In fact, this is a linear map. This is differentiable. Okay. Why is it differentiable? Again, this actually, by the way, requires proof, right? We have not seen a single criterion that tells us when something is differentiable, right? It's not immediately obvious that this is differentiable. This needs proof, but we'll prove it later. Okay, this is differentiable. It turns out there's a nice criterion for doing it. And what is the derivative of this? So the gradient of the first component is what? It's d by dx of y, which is 0. d by dy of y is this. The gradient of the second component is minus 1 and 0. So the derivative matrix is just putting these gradients as rows. Okay. Now let me do one more example. Suppose I take f of r theta as r cos theta and r sin theta. F turns out to be differentiable, All right. We'll prove it later, okay, as we will prove later. But again, what is the derivative? So the derivative is the gradient of the first component. So it's d by dr of this, so it's cos theta, d by d theta of this, so it's minus r sin theta, d by dr of this is sin theta, d by d theta of this is r cos theta. Okay. All right. So this is the derivative matrix of this particular function. All right. Thank you for joining. We are out of time. We'll continue the next time.